Hey everyone, and welcome to today's Explainer. And honestly, I'm thrilled you're here. Today, we're putting all of our focus entirely on multiples, what they are, how they work, and exactly how you can find them. We're going to approach this not just as, basic math calculations, but really as the hidden, repeating rhythms of the world around us. So let's dive right in and start uncovering these patterns.
All right, what are multiples?
Getting our vocabulary straight is the first step. So what exactly is a multiple? Well, it's simply the result you get when you multiply a number by a whole number. Just think of it as the answer you get when you're doing basic multiplication. For instance, 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Those results, 2, 4, and 6, are all multiples of the number 2. It really is that straightforward. Now, if we write these out as a list, the multiples of 2 are 2, 4, 6, 8, 10, 12, and so on. It's literally just skip counting. Multiples go on infinitely too. There is no such thing as a largest multiple of a number because, well, you can always just multiply it by a bigger whole number. Let's check out another set just to train our eyes to spot these numeric patterns. Take the multiples of 5. When we multiply 5 by 1, 2, 3, 4, and 5, we get 5, 10, 15, 20, 25, and it keeps going. As you hear that list, your brain is probably already picking up on a rhythm, right? And that rhythm leads us to a seriously handy rule. Did you catch the pattern there? Every single multiple of 5 ends in either a 0 or a 5. 5, 10, 15, 20.
Finding common multiples.
Okay, let's mix it up. What happens when we compare different sets of numbers? Take the multiples of 3, going continuously, right alongside the multiples of 4. Let's play a quick game of matching here. We're basically looking for numbers that live in both neighborhoods. Scan the two lists. Do you see any numbers popping up in both the 3s and the 4s? Boom! If you spotted 12 and 24, excellent work. Since 12 and 24 appear in both sets, we call them common multiples. A common multiple is exactly what it sounds like, a number that's a multiple of 2 or more different base numbers. And just like regular multiples, these matches go on forever. If we just kept on counting, we'd eventually hit 36, then 48, and so on. Least common multiple, or LCM. So let's funnel this idea down even further. The crucial difference between any random common multiple and the least common multiple is right there in the name. The LCM is the absolute smallest common multiple shared by 2 or more numbers. So while 12, 24, and 36 are all common multiples of 3 and 4, there is only one least common multiple. It's simply the very first match you find. Let's walk through a super logical 3-step hunt to find the LCM, using the numbers 4 and 6. Step 1, list out the first few multiples of 4. 4, 8, 12, 16. Step 2, list out the first few multiples of 6. 6, 12, 18. Okay, step 3. Just scan the lists from left to right to spot the absolute smallest match. In this case, the very first number that pops up in both is 12. So our LCM is 12. Easy, right? Real-life bus schedules. I know what you're probably thinking. When am I literally ever going to use this? Well, understanding multiples isn't just a classroom exercise. It's about uncovering how things sync up in the real world. The LCM is incredibly useful for matching up schedules. Imagine a bus arrives at a station every 10 minutes, and another bus arrives at the exact same station every 15 minutes. If they both just pulled away at the exact same time, when will they arrive together again? To solve this, we just need to find when their arrival rhythms perfectly overlap. Let's map this out using the exact same method we just learned. For the first bus, we list the multiples of 10, arriving at 10, 20, 30, 40, 50, and 60 minutes. For the second bus, we list the multiples of 15, arriving at 15, 30, 45, and 60 minutes. Okay, now the hunt is on for our smallest match. And yep, there it is. The first common multiple for both schedules is 30. That means the least common multiple of 10 and 15 is 30. So we've solved our real-world problem. Those two buses are going to arrive together at the station every 30 minutes. Whenever you're trying to coordinate repeating events, honestly, whether it's setting alarms, tracking bus schedules, or even planetary orbits, the LCM is your best friend. Finally, practice and solutions. All right, we've covered a lot of ground today, and now it's time to actually lock in what you've learned. I want you to try these out for yourself. First, find the first 5 multiples of 7, and then 8. Next, find the least common multiple of 2 and 3, and finally, the LCM of 5 and 10. Go ahead and hit pause on this explainer right now, grab some scrap paper, and write out your solutions. Seriously, give it a shot. I'll be right here when you're ready. Okay, welcome back. Let's see how you did. Your multiples of 7 should be 7, 14, 21, 28, and 35. For 8, you should have 8, 16, 24, 32, and 40. Now for the LCMs. The lowest common match for 2 and 3 is 6. And the LCM of 5 and 10 is simply 10. If you got those right, absolutely fantastic job. And hey, if you missed one, no worries at all. Just review your multiplication tables. You absolutely crushed it today, navigating the rhythms of multiples and using the LCM to solve actual real-world problems. But you know what? This is really just the beginning of the patterns hidden in math. Next time, we are diving into the totally mysterious world of prime numbers, the literal building blocks of all mathematics. What happens when a number stubbornly refuses to be broken down into anything other than itself? It is fascinating stuff, and you won't want to miss it. Keep practicing, stay curious, and I'll catch you in the next explainer.